Hi, my name is Fang, and I'm a PhD student from Institute of Finance and Statistics at University of Bonn in Germany. And in this video, I'm going to present a research that I'm collaboratively doing with my PhD supervisor, Professor Dominic Liebl, who is from the same institute. And the research is entitled Honest Difference in Differences Using Event Study Plots, a Functional Data Approach. So I would like to start my presentation with the motivation behind this research. So our motivation is to conduct honest inference by using event study plots. For those who know a little bit about DID or difference in differences, you may know that event study plots are a common tool that are used by empirical researchers to analyze the treatment effects of an intervention or a policy throughout time. Here is an example of a traditional event study plot that we got from the paper written by Lavenheim in 2019. So they analyzed the treatment effects of DTB laws, or the so-called duty to bargain laws, on female employment. So on this plot, we can see that there are estimates of DID parameter and their confidence intervals at different event times. Mm, for those who know about DID, you may know that in DID research, the parameter of our interest is actually ATT parameter, the so-called average treatment effect on the treated. This is the treatment effect that we are truly interested in. However, ATT parameter is not directly estimable because the computation of ATT would require us to have the potential outcome of treated units as if they were not treated during the post-treatment periods. This is not observable, so that's why ATT parameter is not directly estimable. In DID research, we will try to estimate it via a so-called DID parameter, which measures the difference of observed outcome between treated units and control units at across time t and a reference time point. And this is estimable. So that we need to estimate ATT parameter via a DID parameter, and then use the and then we can use the event study plot of DID parameter for making statistical inference on ATT parameter. However, there are two important assumptions that we need in order to equalize DID parameter and the ATT parameter so that we can use the event study plot of DID parameter to make inference for ATT. And these two important assumptions are no treatment anticipation assumption and parallel trends assumptions. So with these assumptions being satisfied, then we can safely use event study plot of DID parameter to make inference on ATT, or we say to make inference on the average treatment effect on the treated, the true parameter that we are interested in DID research. Okay. So traditionally, people would just check this plot and to see if the confidence interval of DIT parameter at a certain event time contains zero or not. If it contains zero, we say it is not statistically significant. Otherwise, it is statistically significant. So this is how we typically use this traditional event study plot. Okay. However, in our research, we argue that there are two major issues of this traditional event study plot. The first issue is that the confidence intervals on this traditional event study plot are pointwise confidence intervals. Okay, so when we use these pointwise confidence intervals to make inference of treatment effect over multiple time points, then we may have the so-called multiple testing problem. This will lead to wrong family-wise false positive rate and lead to invalid inference. Okay. And in our research, we try to address this issue by consider event time to be continuous and then construct a simultaneous confidence band over the continuous event time from a functional data perspective. By using a simultaneous confidence band, we then can correctly and properly control the family-wise false positive rate over the time span and lead to uniformly valid test. Okay, um, this is how we address the issue of multiple testing problem in the traditional event study plot by drawing a simultaneous confidence band instead of pointwise confidence intervals. Okay, this is how we address the first issue. And the second issue of this traditional event study plot is that it cannot be used for making honest inference on the violation of model assumptions. So previously, I said that there are two important model assumptions for us to equalize ATT parameter and DID parameter so that we can use event study plot of DID parameter to make inference for ATT parameter. And these two important assumptions are no treatment anticipation assumption and parallel trends assumption. However, there is a growing number of literatures becoming interested in the honest inference on the violation of such assumptions. And there are already a series of methodologies developed to tackle with this problem. However, none of them is suitable to be integrated into event study plot. So the empirical researchers could not use a visually convenient event study plot for conducting honest inference on the violation of model assumptions. So in our research, we try to make the event study plot more informative and make it available for empirical researchers to conduct honest inference on the violation of model assumptions. To achieve this goal, we convert the original testing problem with a simple non-hypothesis beta equals to 0 into a new relevance testing problem with a composite non-hypothesis. Okay, I will explain the idea of relevance testing with composite non-hypothesis by continuing this example. So we have a new plot here, and as compared to the previous plot, we now have a simultaneous confidence band, which we use to address the first issue of traditional event study plot, right? So we can see that the simultaneous confidence band we have on this plot is wider than the confidence intervals because it addresses the multiple testing problem. Okay, and we also see a red ribbon in the middle. The red ribbon represents the non-hypothesis, the composite non-hypothesis that we have in our new relevance testing problem. This is by contrast to the single line that we have, single dotted line that we have in the original testing problem with simple non-hypothesis. So instead of using the dotted line, we now use the red ribbon to conduct the honest inference on the violation of model assumptions. And specifically on this plot, we tackle with the violation of no treatment anticipation assumption. More specifically, we now assume that we have treatment anticipation right after the event time -1, and this red ribbon represent the composite non-hypothesis that we have to use to conduct an honest inference when we have treatment anticipation here. Okay, so specifically, we try to see if the red ribbon overlaps with the simultaneous confidence band over a certain time span. If they overlap with each other over a time span, then we say the treatment effect is insignificant over that time span. Otherwise, we say it is significant. So as we can see that there are two short time spans over which the red ribbon does not overlap with the simultaneous confidence band. So we say that over these two short time spans, the treatment effect is still significant even under treatment anticipation starting right after event time -1. Okay. And we also have a plot for the honest inference under violation of parallel trans assumptions. Now we assume that we have parallel trans assumption violations. And the red corn is similar to what we have from is similar to the red ribbon we have on the previous plot. And the red cone here, they also represent the composite non-hypothesis that we have in honest inference under here violation of parallel trans assumptions. And if the red cone overlaps with the simultaneous confidence band that we have, then we say the treatment effects are insignificant over a certain time span. Otherwise, it is significant. And from this plot, we can say that if we have a certain violation of parallel trans assumptions, then the treatment effects become insignificant. Right? Okay, so this is how we can use a very nice and visually understandable event study plot to conduct honest inference on the violations of model assumptions of DID. So here so in our research, we have two tasks to perform. The first task is to construct the simultaneous confidence band of DID parameter for our new event study plot. And the second task is to find out a way to build the red ribbon or the red corn, or here we say they are the bonds. Okay, to construct the bonds, the red ribbon or the red corn for conducting the honest inference. Okay, so let us first solve how to construct the simultaneous confidence band. As I said before, to construct the simultaneous confidence band, we need to construct it from the functional data perspective because we consider event time to be continuous now. And so we would like to link the traditional panel data perspective with our new functional data perspective, and then we can lead to the construction of simultaneous confidence band. Okay. So from a traditional panel data perspective, we say YIT to be a time series which is observable at discrete time point, for example, minus t pre to t post. However, in functional data perspective, we consider the t time to be continuous. So that's why we put t into a bracket to show that the time now is to be considered as continuous. And for the functional data perspective, we also differentiate it via two cases. The first case is called an oracle case. In oracle case, we not only consider the time to be continuous, but we also consider the yi to be completely observed over all t, over the continuous t. However, in practice, it is never the case because, like in practice, even though we can still consider the t to be continuous, but we can only observe it at discrete time point. So that's why we have a second case called observable practical case. In this case, we still consider time to be continuous, but the yi could only be observed at discrete time point, for example, from minus t pre to t post. And this links back to the traditional panel data perspective that we have. Okay. So with the definition of this functional data perspective, we can then define the switching formula between observed outcome and the potential outcome. The definition of switching formula here is similar to what we have in traditional panel data perspective, but we just put t into a bracket to show that time now is considered to be continuous. And the di equals to 1 indicate that the unit I or person I receive the treatment, or di equals to 0 say that the person I does not receive the treatment, so they are in the control group. Okay, then we need to define the ATT. As I said before, ATT is a parameter of interest in DID research. And ATT here is defined in the similar way that we have in traditional panel data perspective, but we just put t into the bracket to show that time here is continuous. And similarly, the potential outcome of the treated units as if they were not treated, like YIT0, is not observed. So ATT is not directly estimable. One thing I need to mention here is ATT is equal to zero for all pre-treatment periods as presumed. Okay, because ATT is not directly estimable. So in DID research, we usually estimated it via DID parameter because DID parameter, they are the difference of observed outcome between treated units, DI equals to 1, and the control units, DI equals to 0 across time t and across time t and a reference time point. Here, the reference time point is 0. This is estimable. So usually we would estimate ATT with DID parameters here. As I said before, if we have no parallel trans assumption, oh no, if we have no treatment anticipation assumption and parallel trans assumption being satisfied, then DID parameter beta t is equal to ATT parameter theta ATT we have here, right? However, if these two assumptions, like if either one of these two assumptions is violated, then beta t is not equal to theta ATT. So we are wondering like what kind of biases does the violation of these model assumptions introduce into the relationship between beta t and theta ATT? So we write out the definition of beta t and we find out that beta t is actually equal to theta ATT minus delta TA plus delta DT. And delta TA here represent the bias that violation of no treatment anticipation assumptions introduced into the relationship between DID and ATT. And delta DT represent the bias that the violation of parallel trans assumption introduced into the relationship between DID and ATT. So these are two biases that the violation of model assumptions introduced into the relationship of beta t and theta ATT. Okay, so as I said before, if the two assumptions are satisfied, then these two deltas are equal to 0, so that beta t, I mean DID parameter is equal to ATT, and we can certainly use the event study plot of DID parameter for making inference on ATT. However, if either of these two assumptions is violated, then we cannot directly use the event study plot of DID parameter for making inference of ATT because like they are not equal to each other if either one of the model assumptions is violated. Okay, so this equation with the biases inside provides the basis for us to find the right ribbon or the right cone in the plot for us to make honest inference on the model on the violation of model assumptions. Okay. Okay. Um, so for now, we need to find a way to construct a simultaneous confidence band of beta t, and then we can use that simultaneous confidence band to conduct honest inference by using by further finding out the way to find out the right ribbon or the right corn for making honest inference, right? Okay. And how to construct a simultaneous confidence band of DID parameter beta t here. We find out that the beta t could be estimated in a function on scalar regression model here. And this model is similar to the two-way fixed effect model that we have in traditional panel data perspective. We just rewrite the model in a way to fit into the function data perspective. And so in the error term, we also have the individual fixed effect lambda I and the temporal fixed effect phi t, as well as the idiosyncratic error term epsilon it here. And similar to what we have in two-way fixed effect model, lambda I and phi t here is allowed to correlate with predictors which include di. So di can be endogenous. And if we directly apply, for example, a least square estimator on this model, then we may suffer from the endogeneity problem. So to tackle with this endogeneity problem, we apply the two-way transformation on the previous model, and then we got a new function on scalar regression model here. And we denote the big guy within the large bracket as gamma t. And we find out that the beta t, the DID parameter that we are concerned about, can be equal to gamma t minus gamma 0. And here, gamma t, we can find out that we can directly apply least square estimator on it because like now the error term does not have any components that are related to the predictors. So we can apply least square estimator without the worry of endogeneity problem. So gamma t can be estimated with a least square estimator on the model, on the new model here. And then the beta t could be estimated by a plugin estimator, and the beta hat t is equal to gamma hat t minus gamma hat 0. So we got an estimator for our DRT parameter. Okay, with this estimator of beta t, and then we need to find out the asymptotic properties of it, like this. Within some proof, we found out that under some regularity assumptions, our estimator beta hat is asymptotically a Gaussian process with covariance function, with the asymptotic covariance function C beta. And C beta defines the relationship of the DID estimator at different time points. And this provides the basis for us to construct the simultaneous compass band. Okay, so it's a very nice theory that we got for our DID estimator. And then we come to the part that how we construct the simultaneous compass band here, as we have the Gaussian process result for our beta estimator here. We can then construct the simultaneous compass band for our DID parameter by using the estimator that we have above based on the Gaussian process properties that we have before. There are many algorithms available for constructing simultaneous compass band, and here we use algorithm from the recent paper written by my supervisor and his collaborator, Liebl and Ramhel, because this algorithm in their paper, because the algorithm in their paper is very fast to compute, and it also has some other very nice properties that we need to have in our paper. We write out the properties that are beneficial for our research in our paper, and you could check the paper for details. But so we use the algorithm in their paper to compute a simultaneous compass band for us for the DID parameter in our research here. And one thing you need to note that the critical value here is variant to time as as contrasted to the constant critical value in pointwise confidence intervals, because like here simultaneous confidence band, it addresses the multiple testing problem. So we have a time variant critical value function, which helps to tackle with the multiple testing problem as before, right? Um, and the and the computation of this critical value function is related to the covariance function that C beta that we derived for the Gaussian process, for the asymptotic Gaussian process in the theory that we got before. Okay, so then now we have a simultaneous compass band for DID parameter, and then we need to proceed to the second task. But before proceeding to the second tasks of honest inference, we need to briefly introduce like how we can use such a simultaneous compass band for doing classic inference under the satisfaction of model assumptions. So what we are truly interested in is if the treatment effects, or we say the ATT, if ATT equals to 0 over the whole time span. So we are interested in such a non-hypothesis. And if we have parallel trans assumption and no treatment anticipation assumptions being satisfied, then we say that the two biases that we introduced before are equal to 0. So the non-hypothesis could be directly translated to the DID, to if the DID parameter is equal to zero or not, right? So then if the non-hypothesis is translated to beta t equals to zero, then we can simply use the simultaneous confidence band we constructed for DID parameter to make inference for ATT because now ATT is the same as DID parameters. So this is how, and this totally addresses the multiple testing problem, and it can control the family-wise false positive rate over the whole time span correctly and make a uniformly valid inference. Okay. Then we proceed to the honest causal inference. So now we are still interested in testing if theta ATT equals to zero during the whole time span. But we cannot simply translate it to beta t equals to zero because beta t is not equal to ATT now with the violation of model assumptions. This is the equation that we got before. When we write out the definition for DID parameter or for beta t, we found out that it is equal to theta ATT minus delta TA plus delta DTT, right? And with the violation of model assumptions, the delta dt and the delta ta may not be equal to zero, so we cannot directly translate theta att equals to zero as beta t equals to zero. There is one additional term that we need to consider. So now we denote delta dt minus delta ta as a whole delta t, and this is the bias that we need to tackle with in honest inference. Okay, this delta t is usually unknown, but in our research we argue that we may use some domain knowledge to come up with a range of the bias, and then we can then transform the original testing problem with a simple non-hypothesis beta equals to zero to a relevance testing problem with a composite non-hypothesis, right? So that means if we cannot know delta t exactly, we need to use a domain knowledge to come up with a range of bias for delta t, and then use it to translate our original non-hypothesis theta att equals to zero a new to a new composite non-hypothesis, which consider the variation of the delta t that we may have. Because we don't know what exactly delta t is, we need to come up with a range of biases for delta t and then use it for doing inference. And this is how we achieve the honest inference under violation of model assumptions, okay? And so we now need to think of a way to determine the bound of delta t, the range of delta t, okay? And we discuss it under the violation of these two model assumptions separately. So at first, we discuss about honest inference under treatment anticipation. This is a violation of the no treatment anticipation assumption. So we discuss it at first. So now we think a parallel trans assumption is held, but now we have treatment anticipation starting right after TA time. TA is the time point right after we have a treatment anticipation. Okay, so because now we have parallel trans assumption, so delta dt is equal to zero, as you can see from the equation, but delta ta is not equal to zero. And in our research, we showed that we can have a point estimate of delta ta as beta ta. Beta ta is the DID parameter at the time point ta. Time point ta is time point right after which we have a treatment anticipation. Okay, so now we can simply estimate beta t under the non-hypothesis as beta ta. Then beta TA is just the DID parameter at time point TA. So we can use our DID estimator from above to estimate it at this point, right? At this time point. And also to get a range of the biases for delta t here, we can simply use the confidence interval of beta t at this time point ta. And so the capitalized S here indicates a control parameter that we want to use for seeing like how large the confidence interval can be. Like if you are confident about the point estimate of beta TA here, then the S could be small. But if you're not so confident about the point estimate beta TA here, then S would be large. You can simply use the critical value from a standard from a T distribution. Okay, so that is how we derive the bound for the biases under the under violation of no treatment anticipation assumption. And here's the plot that I have showed before. So a red ribbon here indicates the range of the biases that we got here, and they should be constant, right? I mean the bounds of the red area should be constant under such a treatment and anticipation. And so this is how we construct. This is how we find out the red ribbon, which represents the non-composite non-hypothesis that we have for honest inference under treatment anticipation. Okay. And secondly, we discuss about the honest inference under differential trends, or we say under violation of parallel trends assumptions. So now we assume that we have no treatment anticipation assumption. So delta TA is equal to 0, but we don't have parallel trends assumptions. So delta DT may not be 0. And um, and now we need to find out a way to find out the range for delta DT. And as we know before that for the pre-treatment period, theta ATT is equal to 0. And delta TA is assumed to be 0 here because we have no anticipation assumption. So that means for pre-treatment periods, beta t is equal to delta dt. So that means we could use the DID parameter at pre-treatment periods for um, for the for the computation of the delta dt at the post-treatment periods, right? And this is how we get a range of bounds for delta dt at the post-treatment periods. We use information of the DID parameter from the pre-treatment periods to construct a bound for delta dt here. And we we make a reference to the very well-known paper written by Roboshkin and Ross in 2023. They discussed the honest inference under parallel trans under violation of parallel trans assumptions. And in reference to their paper, we discussed we discuss two different bounds that we can construct with reference to the DID parameter at pre-treatment periods. So the first bound that we get is like a red corn centered um, around the horizontal the horizontal line of beta equals to 0, and the width of the bound is related to the magnitude of DID parameter at the pre-treatment periods. As I said before, here we need to use some information from the pre-treatment period to decide the range of biases of differential trend at the post-treatment periods. So that's why I say the weights of the red corn is related to the relative magnitudes of DID parameter at the pre-treatment periods. Okay, And this is how the first type of bonds we call relative magnitudes bonds look like on our new event study plot. And the second way to construct a bond is something we call trend restriction bond. So here we can see that this is also a red corn, but it's not centered around the horizontal line of beta equals to zero. Instead, it is centered around a trend that we extrapolate from the pre-trend that we discovered from the pre-treatment periods. As you can see, like the DID parameter from the pre-treatment periods is pointing downward, and we extract the pre-trend, the downward pre-trend, and extrapolate it to the post-treatment periods and make the red corn centered around the trend, and the width of the trend is something that we use to control by a tuning parameter m here. So these are the second type of the bounds that we have for honest inference under differential trends. And for the specific discussion of the bounds, you could just read the paper, and they are written in detail. Okay. So thank you so much for watching the video, and I hope you enjoy it. And in our R package and the paper, we also write about the extension to allow for staggered treatment adoption. Because in my presentation, we only talk about non-staggered treatment adoption, but in our paper, we also talk about the extension to staggered treatment adoptions, and we also allow for adding additional covariance. Thank you so much for watching the video, and please let me know if you're interested in the paper and if you have any further questions. Thank you.